Right, now this is a wee test to look at how liquid and gas within a containment. My lovely assistant Marty here is going to demonstrate how liquid and gas behave in a situation of acceleration. So we're in the car, we've got the bottle sitting nice and level, and I'm going to hand that to Marty, and we're going to look at what happens at points of acceleration. We ready?
Uh-huh.
Now decelerate. Right, we're just going to do that once more. We're in here.
Oh, even in the corner making blocks.
Right.
Dazzle.
Are we ready? You camera on there, Marty? Aye?
Yep.
Ready? 1, 2, 3.
Air goes forward, water goes back. Hitting the brakes,
Accelerate.
water goes forward,
Yep.
air goes back.
So, what we see in the situation there is that the air references the directionality of acceleration. So that being that the water gets thrown to the back of the bottle and the air gets propelled forward, so the air shows you the direction of acceleration. So that's what happens in a sealed unit of liquid and gas, and it displays acceleration and deceleration for us. Now we'll move on to the next part of that. Right, so as we showed in the car, acceleration, the same will happen if Marty forces that bottle down the way. This part here was difficult to capture on camera. I would need to set up apparatus, but anybody can try this. So if you get the bottle with air in it and you accelerate it yourself in any direction, so down, up, you'll see that you'll get a reversal. So the direction that you accelerate the thing in, the air's going to go to the direction of your acceleration. In this case, if Marty's forcing the bottle downwards, the liquid in here goes up the way and the air goes to the bottom. Yeah, you can try that yourself. It's hard to see there, but
If you step back a wee bit and get a wider angle, right, so
you can hear it. You can hear the slosh. You can hear it sloshing. If you try it yourself, you'll see it. It's not really relevant anyway. This is just an extra wee bit we put in. Right. So, yeah. Hopefully we're catching that.
right.
Yeah. So we'll need to do it in the box. What we're going to do in the box. The point is so Mark, the same again. If we hold the bottle like this, and we swing in a circular motion, right? Everybody knows that the water goes to the back and the air goes to the inward point, right? It's the same as in the car. So wherever we've got an acceleration, the air bubble shows us the direction of the acceleration, right? That's very simple and very clear to understand, right? So now what we have to go to, you'll see in these examples when I show it in the box that when we let the object go, there is no displacement, there is no movement of anything. So we'll talk about that in a minute. Right, as we can see in these situations,
It's the level of the water.
right, and we're gonna put this in a box and we're gonna show the camera videoing it better so that the two of them are side by side.
But what you will see is, I can see as I'm dropping it, the water level doesn't change.
No, we'll show that in the box when the camera's right next to it. So the point being to this, that gravity is claimed to be a force or a fictitious force, or you could think of it as a force that acts upon objects that accelerates them towards the earth. Right? Now, as we've just shown and demonstrated, when we have acceleration acting, so in the case of the car is the thing that accelerates, that acts upon me, Marty, and Marty holding the object, which is the bottle with the liquid and the gas within it. So it's being accelerated, and what we see is a shift. We see the water going to the back and the air denoting the directionality of the acceleration. Now, if gravity is claimed to be a force that accelerates objects, well, when we let objects go, we should see the exact same thing happening. We should see the air move to the bottom and the liquid to the top, because the air shows the direction of acceleration. So now we're going to see if that's what actually happens. So, Marty's up here.
Hello.
We've got the glass bottle in the box. We're going to put the camera in next to the box and Marty's going to drop it and I'm going to catch it and we're going to see what we see. So I'll pass that up to you, Marty. Just watch you don't touch the screen because you'll...
Lovely box. And ankle him up. Fingers crossed. Right. 3, 2, 1.
Go again.
Oh, I can smell the log burner up here. 3, 2, 1.
Right. So, as we can see through that, there's absolutely no change. The water and the air remain the way they were. So, what can we conclude? What can we surmise from this? What's your thoughts on it, Marty?
If it was an acceleratory force, then the water would try and move up,
Yeah,
and the air would go down.
as we see.
Aye. If it's a constant force, there would be no difference.
Yeah,
That's just what I would assume.
yeah. So, there you have it. You've been claiming the... I mean, and this is the thing, you can't wriggle out of this. The Globe Earth wants to claim that objects and everything are being accelerated to the Earth at 9.8 metres per second squared. Now, we've just shown what happens in a stage of acceleration. Right? So even... What are you going to do, Marty?
I was going to say that wasn't a stage accelerator, well, apparent acceleration.
Well, this is what I'm saying, this is what it should show.
Sorry.
So if we get that bottle, I just want to see the bottle a minute. Right, there we go. So again, if I go... That's acceleration.
Even if you're doing a longer pace, right? So if we start here where it's level, and if I start accelerating,
Yeah,
it hits the back.
you see it right away.
If I try and take a constant speed,
Yeah, it remains
see anything.
fixed. Right.
so even back the way,
So, we know then that the air denotes the point of motion or acceleration. Now what's the orientation of that? Air at the top, water at the bottom. Therefore, yes,
upwards.
that must be the conclusion.
Know what it is? It's actually this boat that came to Australia.
That's it better now.
Still the same! And
So
you're
no.
saying, if I was to accelerate that, right, rather than just letting it drop at its normal speed,
Yeah, and yeah,
you see the water hitting the top.
yeah. And you can hear it, you can hear the slosh.
Aye.
Because that's what happens in a point of acceleration. Right? This is, it's that simple. You know, we can look at, you know, oh, wait a minute, I've done something to the camera there. Cancel. Right.
Because
So
you're
we can
pointing at me.
practically demonstrate what happens in a situation of acceleration as we've just shown. So Globe Earth proponents are claiming things are being accelerated. The test, the practical demonstration doesn't show that.
And anybody can try that.
Anybody can try that, Marty, exactly. This is
If that's any
repeatable.
magical liquid that's straight out the tap.
This is repeatable, you know, and you can do it in a centrifuge. So if you rotate the bottle, the same happens.
In fact, I'll show that there's nothing wrong. It is pure water.
Yep. Yep. Exactly. Right, matrix. So let's have a discussion about that.
Okay, so this video is for Dell. So Dell, doing a demonstration. I'm gonna show you the demonstration and then I'm gonna basically tell Dell why he's wrong or why you should think differently about these things. Okay? So we had a car. Okay, so what happens when you accelerate the car forward? What did Dell show us? Dell showed us that when you accelerate the car forward and you have a bottle, so pretend the car's filled with water for now, so we'll say this is water and this is air, right? Okay, so do you see that blue? Yeah, okay, kind of. Okay, so this is the water. Now what happens when we accelerate it forward? When we accelerate it forward, the water collects at the back. right? Water collects at the back. This is what it showed us. Okay, no problem. Except he isn't thinking about the physics here. So the physics here tell us that actually, when you think about it, when you're in a car and you accelerate and you don't have your objects strapped down, what happens to your objects? You can hear them clanking around in the boot, right? You can hear them hitting the back of the boot and things, because they're not moving with the reference frame. Do you know what I mean? Well, they are moving with the reference frame, but they're not being accelerated at the same rate as the reference frame until they hit the back, which is why they hit the back. And then when they hit the back, that's when it starts pushing them along. And then there is a force acting on them. Okay, so back to Dell's example. Now, if we have the car again, we accelerate the car forward, right? And we have the water in the car, like this. Okay? Now, if the water is being accelerated at the same rate as the car, as the reference frame, what's going to happen? What do you think I should draw here? If the water is being accelerated at the same rate. So, let's say this is the container wall. The container wall accelerates to here. Okay, these are the container walls. So it moves from here to here, yeah? So as that moves from there to there, if we have water here within this container, let me try and do this again, actually. I'm trying to explain it the best way I can, but I'm not very good at explaining things. Right, so let's say we have the container wall here, and we have the water starting here. Okay, so this is the water. Okay, if we have a force, an acceleration, a force acting on the container, and it accelerates to here in a given time. Okay, so it accelerates to here. If then we also have a force that acts on the water, accelerating it as well as the reference frame, then it's going to still be the same distance. It's not going to crash to the back, it's not going to go to the back at all, because they're both moving at the same rate. And if the container wall is moving at the same rate as the water, then they're not going to have any separation between them. They're always going to have the same distance, all this here, they're always going to have the same distance apart, because they're accelerating at the same rate. So, that's your problem, Dell. Your problem is there was no force acting on the water. The problem is your water in the car is not being accelerated at the same rate. Right, so now if we take it to the drop example. Okay, so there's our container, and we have water in our container with some air at the top. Now, if, again, the container is being accelerated down, so as the top of the container here comes to here, but there is no acceleration on the water is not accelerating, then what's going to happen? The water's going to build up at the back, just like with the car when it crashes, when the things go crashing in the boot. It's going to build up here. And then you are going to have air at the bottom. And that's going to be what your container looks like, if the water's not accelerating. However, if the water is accelerating, then what you're actually going to end up with is, again, we draw our container. The container is accelerating down. It's got water in it and air at the top. Okay, this time the water is going to be accelerating down at the same rate as the container. So as the container top wall here gets to here, this is your container wall, the top of the container, as it moves down, the water inside, so this is where the water starts for the top of the container. Let's just take this bottom one away a minute, because it's going to be a bit confusing. Okay. Okay. I'm just going to do that again. Okay, so as we have the container wall here, and we have the water, and we have the water about this much distance away, so this bit in between is air. We have the water down here, as this container wall accelerates, the top of the container, as the top of the container accelerates down to here, if the water is accelerating at the same rate, you're going to end up with the water here. And there's going to be no displacement at all because they are accelerating at the same rate. They are falling at the same time. If they are falling or accelerating at the same rate, the reference frame and the objects inside, then there is going to be no displacement. It's as simple as that. So now for your other example. Now we have a container. And we have it with water and air again. You got your water in, you got your air in. Now the container is accelerating down at the same rate as the water. So again, as shown, there's going to be no difference because they're falling at the same rate. If you argue this, I can't really help you. But yeah, if they're falling at the same rate, then there's going to be no difference because they're always going to be falling at the same rate. So there's going to be nothing to cause a difference because they're falling at the same rate, they're accelerating at the same rate. So there's going to be nothing to cause a difference in them. Right. Where was I going with this? Oh, yeah. So then Dale says, okay, well, when I drop it, that's what happens, right? Nothing happens, basically. There's no displacement when I drop them. That's because they're accelerating at the same rate, more or less. Okay, so now Dale wants to have the container, have the water and air inside. Okay? So if this water is accelerating down at 9.8, and the container is accelerating down at 9.8, and then Dale wants to introduce an extra force on it, so if he yanks it down, yanks the container down, there's going to be an extra force. So this is the water going down at 9.8. So you got the force on the water, 9.8, and you got the acceleration on the water, 9.8, and you got the acceleration on the container, 9.8. So then Dale wants to add an extra acceleration, an extra force. So if he's adding extra acceleration to the 9.8, let's say he adds 5. So 9.8 meters per second squared, and then he adds an extra 5 meters per second squared, say. Now you've got 2 accelerations down on the container. But you've only got 9.8 meters per second squared on the water. So if we add these together, it's going to be 14.8 meters per second squared, right? So the container's falling down at 14.8 meters per second squared, right? But the water inside is only falling down at 9.8 meters per second squared. So if the container is falling down at 14.8 meters per second squared, and the water inside is falling down at 9.8 meters per second squared, what do you think is going to happen, Dale? One's falling faster than the other, so what's going to happen? The container is falling faster, so the container is going to leave behind the water, which means that the water is going to fly out the back, at the top. You know what I mean? Because it's accelerating down faster, because you accelerated it down faster, but you didn't accelerate the water down faster. You only accelerated the container, which means that the water got left behind. Simple. And this is what you fail to understand with your other examples. With your other examples, like your car, for instance, when your car is accelerating forward, your stuff inside, you're not putting no forces on it. So for your water to remain where it is, like when you fall, when it falls, you're gonna have to keep the acceleration the same. So you're accelerating the reference frame. The object's not attached inside, example the water, will then shoot to the back. Just like when you have in your boot and you accelerate and things start flying around in your boot and hitting the back of the car. Because they're not being forced forward, they're not being accelerated forward at the same rate as the reference frame until they hit the back. That's why they hit the back. And then they hit the back and then they get accelerated forward. But until that point, they have to hit the back because the reference frame is moving. So, for instance, if that doesn't help you at all, so for instance, let's say you have 2 cars, side by side, yeah? You've got 2 cars, no, they're crap looking cars, I can't be bothered to draw properly. Anyway, you have 2 cars and they are accelerating at the same rate Is there going to be any difference? Is one going to go in front of the other? Let's imagine this one's water and this one's a container. They're accelerating at the same rate. Is there going to be any difference? No. Now if we add an extra force on one, an extra acceleration on one, what's going to happen? So let's imagine behind this car there's a truck, and this truck starts pushing the car forward. Now there's more acceleration on this one. So now what's going to happen? The water's going to end up forward while the container remains backwards. So the water's going to go this way because the water's now moving fastward. Because now the water's now moving faster. So it's exactly the same thing. You know what I mean? I'll probably explain that better as well, couldn't I? Okay, so if you have two cars, side by side, these two cars, and they're both accelerating at the same rate, both going the same acceleration, is one going to get in front of the other? Is one going to be left behind? No, it's not easy. That's exactly the scenario when it's falling. It's not getting, the water's not getting left behind because they're accelerating the same rate. The container and the water are going the same rate, which means they're going to stay in the same positions. However, if you then add an extra acceleration onto the container, so you add an extra acceleration onto the container is now going to go faster. So imagine behind this car there was a truck, behind this container car, whatever you want to call it, there's a truck, and if that starts now adding extra force and acceleration onto it, what's going to happen? This is now going to have this is going to now have more acceleration. And because this now has more acceleration, it's going to end up in front of this one, which means that this is going to fly backwards. And that's exactly what you've done with your experiment, Del. What you did was you added an extra force, which made it then accelerate down faster, so obviously things end up going up. Same here, if you have two cars and they accelerate at the same rate, one's not going to end up in front of the other. However, if you then have an extra force added onto the car, so let's say another car behind it pushing it forward, another truck pushing it forward, it's going to end up in front of this one because it's going faster. Because you've added more acceleration, you added more force, and that's exactly what you did when you forced the bottle down. You added more acceleration, so then the water ends up coming out the top because you're accelerating it downwards faster than what the water's accelerating down. It's not that hard, it's quite simple actually.
Rachel, the object is density, so it accelerates down. So density now is a force of acceleration. Are you kidding me on?
Don't do what the Globers do and strawman me saying density's a force. I did not say density was a force, Del. I said relative density disequilibrium is a force, relative density, do you know what I mean? Meaning, not density on its own, relative density. That gives the force. And this can be shown with literally everything and anything. Why does an anvil float in mercury? Because it's less dense than the mercury. Why does a ship float on water? Because it's less dense than the water. Why does a brick fall in air? Because it's more dense than the air. Why does a helium balloon go up in the air? Because it's less dense than the air. Explain these using your Earth accelerating up, Del, and objects not actually accelerating. Please explain that to me.
Listen to yourself. Rachel, I'm not even going to respond to you now. Just go and repeat the experiment and show me it. I encourage you. Go and you make the video and you show your demonstrations. And you show me how I'm wrong, and relative density disequilibriums and density of objects is what makes them accelerate. Fuck off. Fuck off. Stop being absolutely ridiculous. It's people like you that make this whole thing very difficult. Because you're waffling about stuff that you don't even comprehend. Making all sorts of silly assertions and claims about absolute nonsense. Density's now a fucking accelerative force. Fuck off. Jeez, oh man. What a fucking embarrassment. That's why this thing struggles to gain momentum. Because people like you muddy the waters with your nonsense.
People like me? No, it's people like you, Del. The amount of things that you've said that are wrong are unbelievable, to be quite honest. But most of the time I don't actually pick you up on it because at least you're thinking for yourself, and I do actually respect people who think for themselves and don't just go with mainstream consensus. But guess what? One of the things you said during your stream was that the object should fall 9.8 meters in the first second. That's not what 9.8 meters per second means, 9.8 meters per second squared. It does not mean that the object will fall 9.8 meters in the first second. So again, you are wrong there, but yet I'm the one that's muddying the waters and don't know what I'm talking about or whatever. No, Dale, I'm afraid you're just projecting there.
It's up to you to show rates, you know me. I've just shown you practicality.
So that's where I asked him, can you show me acceleration where the object's density and the medium's density are exactly the same? Can you show me that object then accelerating where the object is the same density as the medium? No, of course he can't, can he? Because that's where the acceleration comes from. Here's a video for you to watch, Dale, that you should watch, listen and actually take in. And then tell me why it's wrong and what's wrong about it and why the Earth is actually accelerating up. Go ahead. Link to full video in the description.
And the point I'm trying to make to them is that it's not the difference in the candles and it's not, that makes something float or sink. It's not the difference in the liquids that'll make something float or sink. It's the difference in the density of the floating object and the liquid that you put it into. It's not that this candle is heavier than the other one. It's not that it's more or less dense than the other. It's that the candle, and both of them, are less dense than the liquid they're floating in. And in this case, they're more dense than the liquid they're floating in. So we're comparing the object to the liquid and not to each other.
It's the difference between the object's density and the density of the medium that you put the object in, aka relative density. And that determines whether something goes up or down. Because if it's more dense than the medium you put it in, more dense than the medium, aka relative density, then it will sink. If it's less dense than the medium, then it will rise. It's relative density, Dale.
No.
Why not?